Good morning and thank you for coming along today. Today I'll talk about how we can do good science to better understand earthquakes and tsunamis, and how we can get this good science linked to policy and decision making to be better prepared for disasters. Why is this important? The March 2011 Tohoku earthquake and tsunami demonstrated that even in Japan, where we have some of the best science in the world and some of the best disaster preparedness in the world, we can still be caught unprepared. The Japanese National Seismic Hazard Map was based on the assumption that the subduction zone off northern Japan would rupture in a series of separate moderate-sized earthquakes as outlined by the orange squares. What actually happened was that several segments ruptured at once, causing a much larger earthquake and tsunami than was planned for, as outlined in red, and so we weren't prepared. However, if we look at the literature, we see that other scientists had found geological evidence for similar sized tsunami occurring over a millennia ago. Unfortunately, we saw that this science did not translate into better preparedness, although a full decade had passed before the Tohoku tsunami. So it's in the context of these challenges that Geoscience Australia, through the Australia-Indonesia Facility for Disaster Reduction, is working with Indonesian scientists to do better science and to link this science to better decisions at the national and local level. The Australia-Indonesia Facility for Disaster Reduction, or AIFDR, is a partnership between the Department of Foreign Affairs and Trade and Indonesia's National Disaster Management Agency, BNPB. BNPB is the national agency that is responsible for disaster risk reduction, preparedness, response and recovery in Indonesia. Geoscience Australia works with a range of technical partners, as indicated by their logos at the bottom of this slide, to develop new national and local hazard assessments. This collaborative work strengthens the capacity of Indonesian institutions with a key focus on understanding the threats posed by volcanic ash, tsunami and earthquake. And I gratefully acknowledge the contribution of many colleagues from all these different institutions that have contributed a lot to the work that I will talk about today. By partnering with Indonesia's National Disaster Management Agency, we can see this science informing national policies and guidelines, such as the National Master Plan for Reducing Tsunami Risk, which is informed by a National Tsunami Hazard Assessment that we supported. Through a range of partners, we can engage with local level disaster managers and civil society to provide a pathway for science to inform local level decision making. Development and support of innovative technologies such as InnoSafe and OpenStreetMap makes our science accessible to non-specialists in such a way as to complement their own understanding of their local context. How do we do this? We build capacity in Government of Indonesia science agencies through technical assistance from Geoscience Australia staff. This includes having people based in country posted to the AIFDR office in Jakarta, GA scientists flying in and out, delivery of technical training courses, mentoring, collaboration, support to tertiary education programs both in Australia and Indonesia and linking those programs together. We're also supporting and fostering greater interagency cooperation within Indonesia and facilitating a signing of an MOU between different agencies. Through evaluations of our work, we can see that the mix of activities that we do is greater than the sum of its parts. So Indonesia experiences more earthquakes than any other country in the world. Almost all of the country is very seismically active, with particularly complicated tectonics in the eastern part of the country. In 2010, AIFDR, along with the Public Works Department, supported development of a new National Seismic Hazard Map in order to inform a revision of the National Building Code. This was a major advance forward from the previous 2002 Hazard Map, most notably through inclusion of more onshore shallow crustal faults. This raised the level of hazard in many areas based on the previous hazard map. Much of the science that we've done over the past 5 years has been focused on improving our understanding of earthquake hazard with a view to revising the National Hazard Map. This has included developing a better understanding of ground motion, that is how hard the ground will shake at a given distance from a given earthquake, accounting for the tectonic environment. We have been working to develop a better understanding of the active faults that generate earthquakes. This includes analysing digital elevation models to map the location of faults, geodetic studies to estimate how fast the faults are moving, and paleoseismology to better understand the history of earthquakes on these faults. We have been working to build an embedded capability to do probabilistic seismic hazard assessment in Indonesia. This has been working initially with GA's EQRM software and now transitioning to the Global Earthquake Model's OpenQuake, which is rapidly overtaking EQRM in terms of functionality. And we have been fostering stronger interagency coordination with the goal of bringing the separate components of earthquake hazard science together so that all the expertise in the different institutions is informing the revision of the National Hazard Map. And this has included facilitating signature of a Memorandum of Understanding between 5 different agencies that outlines the roles and responsibilities each of those agencies have in regards to earthquake hazard. We're also testing the earthquake hazard map against the historical record. Earthquake hazard maps are generally developed based on information from instrumentally recorded earthquakes over the past century or so. Historical records of earthquakes therefore provide an independent data set with which we can test the performance of the hazard map. The figure at the top left shows our current understanding of the active faults in Java. The figure on the bottom left plots circles which show the observations of historical earthquake damage from the 17th, 18th and 19th centuries in Java. And so we can see that a number of areas where intense earthquake ground shaking has occur in locations where we haven't mapped a fault and in locations that are now densely populated, including Jakarta. As an example, on the 5th of January 1699, Batavia, as Jakarta was then known, experienced an earthquake so heavy and strong that nothing comparable had ever been known to have occurred there. Buildings collapsed in Batavia and there were dozens of fatalities. Fatalities to building collapse also occurred in southern Sumatra. Numerous landslides were triggered in the mountains to the south of Jakarta, and these appear to have caused damming and subsequent flooding of the watercourses. Interestingly enough, it is noted that this killed all the fish in the rivers except for the carps. We can attempt to find the source of this earthquake by simulating ground shaking from different plausible source models and comparing this with the observed shaking intensities. In this case, we think that the most likely source is a large earthquake occurring deep within the subducting slab beneath Jakarta. We can then use these scenarios to help disaster managers consider their response were a similar event to occur today. We can use the historical record to statistically test the performance of the hazard map. In this figure, we have looked at how often different levels of ground shaking have been exceeded in Jakarta for the period between 1681 and 1877. We can compare these to what is predicted by the 2010 earthquake hazard map. If the hazard map is doing a good job of predicting what we observe, then the red squares, which are the observations, should plot along the red line, and similarly the green triangles should plot along the green line. What we see on the left is that for smaller, lower shaking intensities, the earthquake hazard map predicts more frequent occurrence of shaking than what we actually observe in the historical record. This is not surprising. We wouldn't expect that every moderate shaking event made it into the historical record from this time. However, we do expect that the really big damaging events would make it into the historical record. And if we move to the right here, we can see that the frequency with which big damaging earthquake events occur in Jakarta in that sort of 200-year window is much higher than what we have expected from the hazard map. Therefore, the present hazard map underestimates how often Jakarta will be shaken by large earthquakes. And with the greater Jakarta area having a population that's greater than Australia and New Zealand combined, This obviously has big implications for our understanding of earthquake risk. So this highlights the need to improve our understanding of earthquake hazard. This year, Indonesia's National Seismic Hazard Map will be revised, building on the advances in science that we've been doing over the past 5 years. A key difference between this map and the one produced back in 2010 is that the institutional arrangements for producing this map are much more formalised. A formal structure exists with different agencies taking lead roles on the different components of putting together an earthquake hazard map in line with their responsibilities as outlined in the interagency MOU. If we now turn to consider tsunamis, most of which are of course generated by earthquakes, we can see that on average there is one tsunami every 3 years in Indonesia that causes fatalities. And while the recent focus has been on earthquakes off Sumatra, if we look at the historical record, we see that tsunamis are more frequently occurring in eastern Indonesia than along the Sunda Arc. A national tsunami hazard assessment was undertaken to build a national picture of the tsunami threat that Indonesia faces. This considered both local and regional sources of tsunami and builds on the work done for the National Earthquake Hazard Map. The results show that, consistent with the historical record, that most of Indonesia is exposed to quite a significant tsunami threat. So how is a map like this useful? On April 11, 2012, a magnitude 8.6 earthquake struck off the west coast of Aceh. Fortunately, instead of being a thrust earthquake on the subduction interface, this was a strike-slip earthquake that occurred further out in the oceanic plate and did not generate a large tsunami. It was notable for being the largest strike-slip earthquake ever recorded and generated strong ground shaking that was felt hundreds of kilometres away across most of Sumatra. Tsunami warnings were issued, providing a real-life test of tsunami preparedness. After the event, a team of Japanese and Indonesian researchers undertook a survey of how people responded in Banda Aceh. They found that most people, though not quite all, evacuated inland. However, as they evacuated, they ran into traffic jams. Most people spent between 5 and 20 minutes stuck in traffic as they were trying to evacuate. And this therefore greatly extended the time that it took people to reach their destination. And so what we see is that the majority of people did not reach their destination within the time that it took the 2004 Indian Ocean tsunami to arrive in Aceh. So this is a problem. In response, BNPB, the National Disaster Management Agency, was tasked by the President to develop a national master plan for reducing tsunami risk. A key focus of the master plan was to develop vertical evacuation shelters that would thereby evacuate people above the tsunami rather than inland away from it. These could then be located closer to where people were, reducing evacuation times. Now, BNPB needed to prioritise which areas to focus their efforts in. The new National Tsunami Hazard Map, which was hot off the press at the time, was used to inform which provinces to invest several hundred millions of dollars in. Of course, local information is also needed to inform evacuation planning. Tsunami inundation can be simulated with software like Anuga that's been developed here and at ANU. We can see that if we try and reproduce inundation from historical events and have good elevation data, we can do a good job. The sketch overlay here shows observations from Mount Mary in the island of Flores in eastern Indonesia from a tsunami inundation from 1992. This black line along here shows the inundation limit that was observed in that tsunami. Underneath that are the results of our modelling done with the Anuga software. And you can see that when we have good software, good elevation data, we can produce a result that is quite good. Similarly, we can test different types of elevation data. If we use lower quality elevation data but still okay, we can still get a pretty reasonable result, something that's good enough to plan evacuation. However, if we go to the sort of freely available global elevation data and model the inundation, we can see that we don't produce something very good at all. In fact, we don't even get any inundation. And so this demonstrates that we can use LiDAR, which is very expensive, and get a good result. We can use some cheaper elevation data, such as airborne IFSAR, and get a result that's still useful. But if we use the current generation of freely available global elevation models, such as SRTM, we get a result that is so bad that we would be much better off not having that map at all. So this challenges the common assumption that when you don't have good data, you just use the best available data. And so again, through our partnerships with BNPB and Indonesian technical agencies, this result is informing the National Tsunami Master Plan. In this case, it's informing the development of technical guidelines that determine how you should produce your tsunami inundation maps. And so in this guideline here, it is saying that you should not use SRTM or raster elevation to underpin tsunami inundation models, even if that is all that you have available, because the results can be dangerously misleading. It states in this situation, it's actually better not to have a map than a map that is wrong, that can lead to wrong decisions being made. So I've shown how some of the work that we are doing is influencing national level policies and development of standards and guidelines. Does this translate to a difference on the ground? We've been working with the Geology Agency of Indonesia to produce provincial scale earthquake hazard maps. These are created using EKRM and include local site amplification effects. The green areas show provinces where we have worked directly with staff from the Geology Agency together to produce hazard maps. The purple areas show where these same staff have used this new capability to produce earthquake hazard maps independently of GA, demonstrating the sustainability of the capacity in the agency. The yellow areas are being done as we speak to be published this year. These maps are helping local disaster managers understand their earthquake risk. South Sulawesi experiences less earthquakes than other parts of Sulawesi, and local disaster managers have told us that they're not concerned about earthquakes and that floods are their problem. Floods happen every year, they happen frequently, that's what they worry about. Nevertheless, there are some active faults that cut through the province of South Sulawesi, and therefore in some areas there is quite high earthquake hazard. So even though that earthquakes don't occur as frequently as floods, they can still pose a serious threat and should be prepared for. We were able to use this provincial earthquake hazard map in the impact assessment tool that we have developed called InnerSafe to help local disaster managers understand potential earthquake impacts. Through this process, they were able to compare the potential impacts of floods with the potential impact of earthquakes. And so they came to understand that they should be preparing not only for floods, but also for earthquakes. I'll now present a case study from the Mentawai Islands. This is a chain of 4 small islands off the coast of West Sumatra that sits directly above the Mentawai segment of the Sunda megathrust. Over 15 years of scientific research has been done here, led by a Kerry Seas group from the Earth Observatory Singapore, that has unravelled the history of great earthquakes along the Mentawai segment of the Sunda megathrust. Between earthquakes, the subducting plate pulls the front of the overriding plate downwards. As this happens, the Mentawai Islands subside and the corals that fringe these islands slowly grow upwards to keep pace with the subsidence growing towards the water surface. When an earthquake occurs, the outer part of the overriding plate flips up and the islands are lifted out of the water. And these corals are lifted out of the water with the islands and therefore die back. By measuring and dating these uplifts, scientists have been able to determine the history of great earthquakes on the Mentawai segment of the Sunda megathrust. And so it turns out, if you look at this pattern over the last 700 years or so, that we get these periodic uplifts occurring approximately every 200 years. Either one great earthquake or a pair of moderately sized earthquakes have occurred, still capable of generating significant tsunami. And so this research in its early days began to highlight the potential for large tsunami in the Indian Ocean. And most famously, our own Phil Cummins' Elsevier News article published just a few months before the 2004 Indian Ocean tsunami sounded a warning for the potential of large earthquakes to generate tsunami off Sumatra based on some of this research. But the Mentawai segment still hasn't ruptured. And so we can see Kerry C making a similar prediction, this time in 2008, saying that to those living in harm's way on the coast of Western Sumatra, it should be useful to know that the next great earthquake and tsunami are likely to occur within the next few decades, well within the lifetimes of children and young adults living there now. So this image here shows the history of great earthquakes along this Sumatran part of the Sunda megathrust. The orange up here is the southern part of the rupture zone of the 2004 Indian Ocean tsunami. The red is the 2005 Nias earthquake. The green and yellow are the 2007 Bengkulu earthquakes. 2010 is the blue here is the 2010 Mentawai Islands earthquake, which generated a locally large tsunami that killed about 500 people. But we can see this patch in here, where we've had earthquakes in 1797 and 1833, still hasn't ruptured. So none of these smaller events here have been the big earthquake that people are expecting to happen. And so the threat of this big earthquake has been fairly well publicised in Indonesia, and this really demanded a response from government. The 2011 Tohoku earthquake further demonstrated the need for government to be prepared. So BNPB came to us requesting us to define a worst-case scenario for the Mentawai segment of the megathrust. The scenario would be used to support an international disaster response exercise and would also inform evacuation planning at the local level. And so without making any claims to have defined a worst-case scenario, I'll take you through the work we did and how it was used at the local level. So based on the coral paleogeodetic data, we can see that the cumulative pattern of uplift for each event or pair of events that occur every 200 years or so is fairly similar for at least the past 700 years. So based on this kind of similarity of the ruptures on this segment of the subduction zone, we attempted to generate a whole bunch of different earthquake source models that were consistent with the vertical deformation recorded in the coral record. And so we were able to randomly generate different heterogeneous rough slip distributions and find models that were consistent with the coral uplift data. And so we were able to simulate about 15 million different random simulations and then find about 5,000 of those that were consistent, generated vertical deformation that was consistent with what's recorded in the coral data. On the right is a couple of examples of two of these models that do fit the data. You can see here is the slip distribution. So the blue is lower levels of slip up to red wing, about 20 or 30 metres of slip on different parts of the fault. And what we can see is that this earthquake, which doesn't have a lot of slip, can still generate some deformation that's consistent with what we observe in the coral record. This earthquake here, which has a high patch of slip out near the trench, can also generate vertical deformation along the islands where we have data that is consistent with the coral data. But this patch of high slip out here is therefore generating great vertical deformation out here, and that can cause a locally very big tsunami. And so at the time we were doing this, Leslie Wybon kept telling us that we weren't using the NCI's new Ragen supercomputer enough, that we needed to work it harder. And so we were able to take the opportunity to simulate thousands of inundation for thousands of different scenarios, rather than just the handful that we might have typically used for doing tsunami inundation modelling. And so if we look at the results, taking a couple of examples from the island of Sipora, we can see that we can build a more complete picture of the potential inundation zone. This red line here, that plots fairly close to the coast, is what you get if you only simulate inundation from an earthquake scenario that is a best fit to the coral data. We know that this problem is quite poorly constrained and that there are many other potential rupture models that are also consistent with the coral paleogeodetic data. And so if we start to simulate inundation from these range of different scenarios that are consistent with the geological evidence, we end up with a much larger inundation footprint, and we can look at how many of these models inundate any particular point And so we can define a more robust evacuation zone. And again, I'm not going to say this is the worst case, but we have a lot more confidence in it than we do just on the single scenario. So these results then feed into the official tsunami hazard map that was produced by the Geology Agency. And we can also develop local inundation maps for community engagement. And so these maps informed local government workshops run by the Indonesian Institute of Sciences, allowing this information to be considered in the formation of their disaster management plans. And so in the words of Pak Mahyudin, the Secretary of Tuapajet Village in Sephora Islands, he says, "With these maps, we will prepare ourselves to identify evacuation locations to save ourselves. We're very thankful for these maps, which are not a negative thing or to scare the community, but give us knowledge that if a very strong natural disaster occurs later, then these maps will make us more careful, more ready to face the disaster." We also worked with the local leaders to help them map their community. This new spatial information could then be integrated with the hazard information that we had provided to develop evacuation plans, including to identify which buildings would be used as evacuation shelters. And so this process of participatory mapping built genuine ownership over the process of developing an evacuation plan by the community. And so we can see from this example a number of key points that this work, firstly, that the science is built on over 15 years of fundamental research to inform the hazard assessment. We can then utilise high-performance computing to consider a much greater range of uncertainty than what we have previously done. When we go out into the field, we see that disaster managers are making decisions based on the information they have now. If we come with new information that can be incorporated, but they are making decisions right now. There are challenges at the local level in terms of the local level capacities and how much time and effort they can really put into disaster risk reduction when there's so many other competing priorities. And participation is critical in disaster risk reduction. Participatory mapping builds ownership and understanding of spatial information, both in terms of the location and their community itself and the hazard information that we provide. So let us now move further east to consider the Java megathrust. We have had smaller events here in 1994 and 2006, but no great subduction zone earthquakes are known from the Java megathrust. And historically, Java was actually assumed not to have large events, based on now well-discredited theories relating the age of the subducting slab and the rate of plate convergence to the maximum magnitude possible. In fact, if we look at these old plots, we see that Java plots right near Tohoku. So we know that the theory that said Java couldn't have a really big earthquake is wrong. What we don't know is whether an earthquake on the scale of what we saw off Tohoku has ever occurred off the coast of Java. So what does this mean? We can compare here, on the left, inundation from a Tohoku-like earthquake for Central Java, with on the right, inundation from what we might have a few years ago thought was the maximum magnitude possible off Java. So on the left we have about 45 metres of slip occurring on the fault, and on the right we have about 6 metres of slip occurring. And the difference, of course, is dramatic. Between, we have on the right we just have a very small amount of inundation, on the left we have several kilometres. So this uncertainty translates into massive uncertainty for disaster managers. We can use the InnoSafe impact assessment tool to estimate the population that would need to be evacuated were either one of these events to occur. And so we can see again that the difference in terms of disaster management is enormous. And the problem, if we were to have a Tohoku-style event off this part of Central Java, is about 300 times larger. If we consider such an event occurring further east off the coast of Bali, we can look at some results done by some German colleagues a few years ago, considering a magnitude 9 scenario. And we can see that many areas that are familiar to us, the airport, Kuta Beach, Sanur, are under a lot of water in this scenario. And so with 16,000 Australians visiting Bali every year, and quite a few of them spending time at the beach, such an event could easily be Australia's worst natural disaster before the tsunami wave had even reached Australia. Were a Tohoku magnitude event to occur off Java or Bali, impacts could be expected down Australia's west coast. Modelling done for Australia's west coast back in 2006 was quite conservative, considering magnitude 9 to 9.3 events combined with high tides. Yet even despite this conservatism, the amount of slip on the earthquake fault that we saw for the Tohoku event is greater than what we have modelled previously. We don't yet know exactly what difference this will make to our current understanding, particularly in terms of our understanding of the economic impacts to the ports along Australia's west coast. And so we don't know if such an event has occurred in the past. Geological investigations along the south coast of Java have found a number of sand sheets that are plausibly deposited by past tsunami. These suggest that tsunami do occur frequently off the south coast of Java, but at present we don't have enough evidence to correlate these deposits from different locations along Java to really get an understanding of just how big these events were. In addition, we have some interesting work by Professor Tony Reid, who's a historian at the ANU, who has examined some of the Javanese chronicles chronicling the history of Java and has suggesting that there may have been a large tsunami impacting the south coast of central Java in the 16th century. And this links, interestingly, to the mythic Queen of the South Sea, who in Javanese histories is responsible for dangerous events along Java's south coast and for the legitimisation of kings and rulers. So we are yet to determine whether this links with the paleo-tsunami deposits. But using geological and historical evidence presents one promising approach for reducing the uncertainty around the history of great megathrust earthquakes along the Java Trench. So to summarise where we're at so far, since 2009, AIFDR has supported Australian and Indonesian scientists to work together to improve our understanding of earthquakes and tsunamis in Indonesia. Long-term investments in science mean our understanding is much more advanced in Sumatra than it is for Java and for eastern Indonesia. Close engagement between scientists and disaster managers at national and local levels has provided pathways for science to inform decisions as they are being made. Through this, science is informing national policies, prioritisation of spending and disaster management initiatives, and the development of national standards and guidelines. We can also see how these partnerships, along with innovative technologies such as InnoSafe, are seeing science being used to inform disaster planning at the local level. I'll finish today with these two images. In the left image, we have Ibu Dewi, the woman in the middle holding her son. She lives in the Mentawai Islands. The house behind her is a new house that is being built up on a hill. As a result of learning about the tsunami threat faced, her family has decided to move back from the coast. Local landowners are helping to make land cheaply available for people wanting to move away from the coast. Here we see that scientific information combined with good policy interventions is leading to better disaster preparedness. The image on the right is from Banda Aceh. In 2004, this area was under about 10 metres of water, about the height of the building we're in. The photo shows a house that has been built as part of the reconstruction effort following the Indian Ocean tsunami. You can see that at high tide, the ocean breaches the breakwater to surround the house. And while we need no more science beyond what we saw in 2004 to tell us that this location is exposed to tsunami hazard, we can see that in this instance, a breakdown of policy has resulted in the most exposed locations being re-inhabited. So these images really underscore that we don't just need good science, but we need to ensure that it is being used to inform decisions. When we do good science and see it linked to decision making, we can see communities being demonstrably safer, better prepared for earthquakes and tsunamis. This is immensely challenging, yet the work that GA and our partners have done in Indonesia shows that over time we can do better science, and that science can inform key disaster management decisions at national and local levels. Thank you very much for coming today, and I'm happy to take any questions.